Let's dive right in. Let me welcome you again to today's webinar on automated labs for material discovery from concept to market. We have two presenters today, Dr. Stuart Miller and Aaike Vugt. And I'm Aaike. I'll be your host for the day. I have a background in high throughput electrocatalysis and electrochemistry, and I'm currently working as the product manager for self-driving lab applications at VSParticle. Let me briefly run you through today's agenda. So we'll start with an introduction about the company and a small speaker biography, and then we move on to our presentations for the day. We have our first presentation by Dr. Stuart Miller from MDRI about the search for sustainable energy materials using autonomous labs. And then we have our second presentation by Aaike Vugt, VSParticle CEO, about the technology and about unlocking a new paradigm in the thin film nanoporous layers for energy technologies. And finally, we have a live Q&A session. And I would highly encourage you guys to please post your questions in the chat to Stuart and Aaike, as and when you have them, so that we can pick that up during the live Q&A. Moving on. So just a small introduction about us. VSParticle, we are a leading supplier of next generation tools for nanoparticle synthesis and deposition. And we aim to provide the best in class nanoporous layers using an automated synthesis technology to help our customers accelerate energy material discovery. And we have our esteemed customer from MDRI, who recently installed our nanoprinter to leverage our technology to create the most advanced autonomous labs for material discovery. And from MDRI, today we have Stuart Miller, and it's truly an honor to welcome you, Stuart, to today's webinar, who is no doubt an expert in accelerated material discovery. He's the Executive Director at Material Discovery Research Institute, MDRI, which branched from Underwriters Laboratories Research Institute and was established by Stuart in 2022. It is a state-of-the-art material science laboratory which focuses on accelerated material discovery to provide novel solutions for global challenges such as renewable energy generation and storage, water harvesting and purification, and carbon capture technologies. Stuart, would you like to say hi to our audience?
Yes, good morning, good afternoon, good evening to everyone. It's a pleasure to be here.
Thanks a lot, Stuart. We really appreciate your presence today. And we have a next speaker who is the CEO of VSParticle, Aaike Vugt, who's an extremely passionate and forward-thinking person who since a very young age was motivated by the mission of energy transition. With an in-depth understanding of the importance for scale and rapid innovation within the field of advanced materials, he co-founded VSParticle during his final year at the Delft University of Technology with a clear mission of unlocking a century of material innovation in the next decade. And Aaike, would you also like to say hi to the audience?
Hi, and thanks again, Stuart, for joining us today on the webinar.
Thank you, Aaike. We are really happy to have you both today. Now, before we deep dive into today's presentation, I would really like to introduce the topic in a small way. So I hope that you would all agree with me that the search for sustainable energy materials requires the help from tools like automation and AI due to the complexity of the material space that we are dealing with. So we have quite some parameters to optimize like porosity, composition, microstructure, and so on, which opens up a vast material space from which we need to funnel down to the best candidates, to the best materials. Right, and taking the help of these tools like AI, and we are able to generate these predictive models with the help of large experimental data sets. And that is the future that guides the future of material development. And in this context, I would like to ask you a question. We have a poll question coming up your way. The poll question would appear on the screen right now. And please take your time to vote, to cast your votes. How large do you think this experimental data set should be in order to be able to accurately predict the best materials or the most optimal materials? Please feel free to cast your guesses. I'll give you a couple more seconds to think. Yeah, I really see how well versed you guys are in the topic from the poll responses, which is great. All right. I hope you all guys have all voted. So yes, the right answer is we need something like a 50,000 to 100,000 candidates in order to be able to develop these predictive models in an accurate way. And this actually opens up a question. Is it really that easy to create such large experimental data sets in order to train these AI models? And that is a question, one of the questions, in fact, which we would be having answered from Stuart and Aaike today. They will explain about how we can create these large experimental data sets with like 100,000 material candidates in a relatively short time. So I think it's now time to move to our first presentation. And Stuart, I leave it to you.
Thank you. Okay, so hopefully I have control of the screen. I'm just going to try and advance to the next slide.
Yeah.
Okay, great, thank you. So thank you for the introduction. And again, good morning, good afternoon, good evening. My name is Stu Miller. I'm the Executive Director for the Materials Discovery Research Institute, which is one of the 5 research institutes in Underwriters Laboratories Research Institutes. And I think I will address the elephant in the room immediately. So for those on the call that are aware of who UL are, they may be more familiar with a company that does testing, inspection, and certification. So maybe you've seen some of the testing that's been done for Christmas tree lights or microwave doors or the pump at the gas station. This company, this organization has went through a reorganization in the past decade or so. It's a 130-year-old company founded in 1894 by William Henry Merrill. Started as a not-for-profit company, and in 2012 we established our for-profit entity, which is UL Solutions, and we kept our not-for-profit brand, our 501c3. In 2021 we established a second not-for-profit, a 501c4, which is UL Standards and Engagements. And the 3 parts of these organizations make up our one company, one organization, enterprise, which is UL. Now, for me, and today I'm going to specifically talk to you about Underwriters Laboratories Research Institutes. We are a self-funded entity. There was an endowment that was announced in 2022 and further endowments that were announced since then. So we aren't required to go out and chase any funding opportunities. And it means the funding opportunities we do apply for really align with our science and our safety science mission. As I go on and talk about who we are, we have these 5 institutes that I'll introduce you to, but we are driven by 3 grand challenge commitments. And if I could ask you to take away anything from this slide, it's our mission is to make the world safer through research and engagement and be the world's leading safety science research organization. To do this, we focus our efforts in these 3 areas, which is resilience for a sustainable future, individual and societal health in the 21st century, and safety at the human-digital interface. Now, I'm not going to speak today about safety at the human-digital interface, but we do have an institute, our Digital Safety Research Institute, that focuses heavily in this area, emerging safety threats that may be aligned with artificial intelligence or looking at bias in algorithms or deep fakes. What I will speak about is resilience for a sustainable future in the individual and societal health in the 21st century. The resilience for a sustainable future really looks at some of the safety concerns that come around when you start to consider climate science and climate change. So this could be looking at decarbonisation of the grid. It could be looking at removing air pollutants, whether these are carbon air pollutants or toxic gas air pollutants. And the individual and societal health, we have a strong effort there that focuses on removal of contaminants either from the air or water. The right to clean, safe and equitable drinking water across the globe is a large thrust for the MDRI. Our research institutes are actually 5 institutes and 3 offices. I do encourage people to go online and learn more about each of these institutes, and these are spread throughout the United States, either in separate states, or our Digital Safety Research Institute is primarily online. Our Chemical Insights is in Marietta in Atlanta. Electrochemical is in Texas. Our Fire Safety is in Maryland. And then Materials Discovery is in Skokie, Illinois. And we're supported by our Office of Partnership, our Office of Research, Education and Experience, and our Library Information Services. And all of these really come together to provide this core infrastructure that we need to be able to address emerging safety science issues. For the Materials Discovery Research Institute, what we're trying to do is have a proactive approach to how we deal with emerging safety threats, specifically aligned with these 2 first grand challenge commitments, so resilience for a sustainable future and individual and societal health in the 21st century. And as you think about the impact of materials over the past century, these have really been at the cornerstones of innovation and bringing people out of poverty, providing better health for individuals. For those material scientists that are online, this cyclical feedback diagram should be fairly well known. The way that we look at the world is we identify the problem that we would like to be able to address, we synthesize our materials, characterize, understand the structure and the properties of the materials, how this is processed, and then we go back to synthesis to improve the performance and look for how we can benefit in that area. I think where the MDRI differs is we've had this really unique opportunity to create an institute from nothing. It's been a blank canvas approach. And before we went into the lab, the first thing that we said is the most important metric that we produce at the MDRI is data. And we spent now about 20 months establishing our data architecture before any experiment was done. Now, when you go into our labs, which I'll come to later in this presentation, they were recently opened, the first thing that we do is we pick up an iPad. So every aspect of data is captured. We can tell you the date and time you did your experiment, but the temperature in the lab on that day, the relative humidity, who ordered the chemical, which shelf did it sit on, who was the last person to use it. And we really lean into this approach that capturing every part of data is incredibly important. The other thing that we do, which maybe isn't unique from an industrial perspective, but is a little bit different from an academic point of view, is before we start the experiments, we really look at what the should-haves and the must-haves are. So we are focused on ensuring that we can get the most effective solution to the problem at the appropriate price point. And bringing in the economics of what we're doing before we start experiments is really critically important. So the MDRI is 20,000 square foot, which is based in the Illinois Science and Technology Park. We are probably about 10 miles from Chicago. We're conveniently located. We're about 5 miles from Northwestern University. We are maybe 15 miles from the University of Chicago. Again, another 15 to 20 miles from Argonne National Lab. And Chicago's a really great area. It's got thriving industry in the materials and chemistry space, and also top universities in the world that we have really great relationships with, collaborations with, and access to the talent that's there. We have, as I said, 20,000 square foot in the 3rd floor, and we're currently renovating about 3,500 square foot in the basement of the building. And what this has given us is a digital first approach with a state-of-the-art automation lab. So And I'll go into how automation and high throughputs beyond the nanoprinter, the VSP nanoprinter that we have, and how it really drives the setting of our lab. We have 4 labs that are entirely dedicated to the synthesis of materials. And we have 2 labs that are dedicated to characterization, which is materials characterization, electrochemical characterization, and surface characterization, all coming together to really give us a world-class digital first facility. And with that, I seem to be missing. Okay. So with that, we have, there we go. With that, we focus on 4 priority research initiatives within the Institute. And these funnel into our Grand Challenge commitments. As I said, predominantly for MDRI, this aligns with the resilience for a sustainable future and in individual and societal health in the 21st century. But our 4 areas of research in the Institute really focus on sustainable energy generation and storage. So this is really incredibly important when you think about decarbonisation of the grid and what the world has to be able to do to meet the 2030 and 2050 deadlines that have been set by the IPCC and guidelines set by the IEA. We focus on deep energy storage solutions, alternatives to oil and gas. The second, and I'm sorry that the title for the second one's not there, but this is eco-remediation. So, and the way to think about this is we've been, as a global community, relying on energy from oil and gas and beyond energy from oil and gas for over 170 years. And this has created chemical imbalances in our air and in our water. And we develop materials that really look to address, to be able to provide clean, safe drinking water in areas that it might not be economically beneficial for large multinational corporations to be able to go in and address these issues. But from a humanitarian point of view, and you can think of areas in South America, areas in sub-Saharan Africa, where providing safe drinking water for communities is vital for their growth and development. We also look at translational research and prototype development. This is really important for us because from the experience that I've had in my career, looking at developing a material in a lab-based setting is incredibly important, and this is really the first stage of technology development. But bringing that material into a device, and a device that can be evaluated in a real-world situation, adds an immense amount of value, and it embraces this fail-fast approach where we can take our materials and we can learn so much more by, maybe we want to go to deploy materials in Kenya for atmospheric water harvesting or for water purification. Maybe we want to look at creating large-scale electrolyzers or PM fuel cells, to be able to say that not only can we get high efficiency at a 5 centimeter squared or a 50 centimeter squared size, but we can actually move into short stacks and full stacks for these devices. And then lastly, the last research thrust that we have really focuses on what we're talking about here today. And this is the accelerated research methodologies. And I think I took down a note of Aaike's mission there to be able to deliver a century's worth of innovation within a decade. And that really is where we focus on how can we get more from our research on a much quicker timescale, because the world can't wait for the things that need to happen. Deadlines have been set and the scientific community needs to be able to deliver. And the way that we do this is these 4 priority initiatives that really come to fruition in these 3 areas. We're guided heavily by computation and theoretical chemistry. So we have a group that focuses on trying to understand the properties of materials and the properties of the materials in their working environment from a computational, very fundamental DFT approach. Then we can begin to take some of the findings, the understandings that we have from that approach into our high throughput automation. And we have the capabilities Probably. I mean, we have 3 large automated synthesis platforms, and one of them shown in the image next to the VSParticle there. And we could generate millions of data, millions of materials that we can derive data from in a year. From a synthetic point of view, the challenge becomes, how do you characterize the materials at this large scale? And this is something that we are working on with partners. And then the fabrication of devices, and as I said, this basement space to us to be able to take our innovations into prototype development is critically important. And I wanted to give you an example. I've got 2 different examples here. I'm thinking about material synthesis and why high throughput accelerated methodologies really is a game changer to reduce the time from inception of material through to leveraging that material in a real world environment. The left-hand side, and maybe there's materials chemists that are online would be familiar with these. These are acid digestion vessels. This was how I spent the majority of my career working in these vessels. The right-hand side is an 8x12 high throughput array, given 96 wells there. And I spent a lot of time working with these during my time in Institut Lavoisier in France. If you just look at, this is a really, really rough comparison, but if you look at how you can compare each of these materials, and I took a very simple 3-component metal organic framework as a price comparison point. If I was doing high-level studies with these metal organic frameworks, you can reduce your volume in the high throughput. And when you begin to leverage mechanical dispension, automated mechanical gravimetric dispension technology, volumetric dispension technology, you can be much more accurate at lower volumes and lower masses that you are weighing into these vessels. So your daily throughput, and yeah, I'm sure there's people that are online that are much more proficient in the lab than I am, but I would be working at about 8 vessels in a day. I'd have 8 in the oven, 8 cleaning, and 8 on the desk. And that sort of cyclic approach to keeping my research moving is time consuming. It gives you about 2,000 experiments in a year, and it gives you time to be able to cultivate and analyze that data as well. But if you just look at the cost for 1,000 reactions, there's this orders of magnitude difference between the high throughput and the traditional. This is not taking into consideration the outlay of the capex of the high throughput equipment, but it does get you to a point where that capex is rewarded and pay off quite quickly. And then the time to be able to complete these reactions. I think the easiest way to look at this is a side-by-side comparison. So if this high throughput methodology was operating the same hours per day as I would operate in a lab, you'd probably get in the region, if you were not thinking too much about your data, you'd get in the region of about 250,000 experiments done on an annual basis. These instruments can run at the weekends, during holidays, and at night. So that number could probably be increased quite a bit there. I think that when you look at data like this, or you look at experiments like this, the real thing is the questions that you ask change, because you need to be a lot more meaningful and pointed with your experiments and lean into the data much, much more. Another example that I wanted to bring to this was actually looking at the nano printer just before I talk about the importance of data. And we've had the nano printer installed in our lab for a few months now. It's an incredible instrument, and we're really excited with the future possibilities and designing our research thrusts in our renewable energy generation and storage around a nano printer. But I wanted to sort of take a step back and get to maybe the question that was asked at the beginning of the presentation this morning. How much data do we need? If you looked at what we have at the moment is a 2-source 2 G1 units that are on the nanoparticle. And at the moment we have about 10 metal sources. And these metal sources, if we take, for example, copper, we have 2 copper rods, one fitting in each of the G1 units. So it could give us a possibility of 55 different combinations of these metal sources. Could be copper, copper, could be copper, silver, silver, gold. We sort of came to about 5 variables that we could manipulate. The current that we use, the printing nozzle speed, printing nozzle distance, the carrier gas type, and the carrier flow rates. There might be more. It might be some of these are overkill, but it's just as an example that I'm giving here. And if we look at these 5 variables and we use a low, medium, high setting so that you can map out your full factorial DOE, it gives you about 13,500 possible total experimental combinations that you can look at on these 2 metals. And if you make some assumptions, you can maybe do 15 minutes per print, 2 prints per day, 6 hours per run, and you run 50 weeks for the year, it's going to take you just over a year to complete every single one of these experiments, if everything goes well. And I think that's a big caveat that's there. If we then say, well, what I'm actually interested in is more than 2 metals, and I'm interested in targeting a multi-component product from this. If I look at 4 metals using the same experimental design, that's going to take me about 18.5 years. And if I look at 6 or 8 metals, it can run up to 150 years roughly. This is why we really need to lean into the data. And MDRI, the largest focus that we've had, and I mentioned earlier in the presentation, we spent over 18 months, about 20 months now, cultivating how we collect data. It's because we generate so much of it and we're in complete control of that data. We know, as I said, the lab of chemicals, the inventory, we do the experimental planning, and we also, one of the things that's typically traditionally done is we don't report bad data. And when you start to lean into machine learning capabilities and you look to leverage Bayesian optimization, the bad data or the data that doesn't give you the successful experiment is just as valuable as the good data, because the goal here is to take that 18 years and get it down to 6 months or 18 months, really reduce the time. So that's why we've spent so much time to be able to come in here, because we promote the consistency in our data, and overall we believe that there's a substantial saving in time to be able to get to shorten that discovery timeline for the key materials that we need. Just to finish, we did have our ribbon cutting ceremony just over a month ago, and I couldn't be prouder than the group of individuals that I work with. One of the things, and I'm sort of caveating this because I don't want any complicated questions in the lab, in the chat. One of the things that I have is an amazing group of people, every single one of them smarter than me at what they do. So, and it's a key thing that we brought in. Our electrochemical or our renewable energy generation and storage group is led by Dr. Jeff Wu, and you can see Jeff and Uzoma here, who have been pivotal to the work that's happened in this area. So thankful and grateful for these individuals. And as we move into next year, there's going to be new opportunities that arise to be able to be onboarded in the Institute. So for that, I'd like to be able to thank you for your time. I'm going to leave that there. And I think Aaike, is it?
Yeah, I will do. Thank you, Stuart. Thanks a lot for that very interesting talk. Thank you for sharing your insights about your approach of research at MDRI and how important it is to generate this large amount of data to accelerate material discovery. Thanks a lot. Before we jump into Aaike's presentation, I have a small question for you guys coming up. It's poll time again. So sticking to this topic, it's a question that comes up a lot, I think. You will see the question popping up on the screen right now. We talk about automation a lot. We talk about these self-driving labs. What level of human interaction would you prefer in your automated lab? I know that it's quite a debatable kind of question, so feel free to post your points also in the chat if you feel like. We can maybe have a chance to pick that up during our live Q&A. Well, yeah, it's a very balanced kind of response that I see here. All right, thank you for insights. It's time for a second presentation. Aaike, I leave the floor to you.
Thanks, Aaike. And thanks, Stuart, for the nice introduction and of the great work that you were doing in setting up this, I would say, one of the most advanced infrastructures in the inorganic space that I've seen so far. And I'm really looking forward to maybe do a follow-on webinar next year with much more in-depth results in testing materials and showing what the capacity of the lab is really able to do. So as most of you know, my name is Aaike van Vugt, co-founder and CEO of VSParticle. And next to the presentation of Stuart, I would like to give you an update on where we as a company stand toward this field of creating AI-enabled predictive models. So maybe first of all, the vision of VSP. So we believe that solutions to big issues are urgently needed. We need to provide a lot of material innovation in the next 10 years to make climate crisis a solved problem. On the other side, we strongly believe so that new materials will enable impactful solutions, so that we need to provide those solutions through the development of more innovative materials. However, most of those materials are not yet developed, and the timeline to develop a new material is on average 15 years plus. So we really believe that we need to crack this problem and try to reduce the time to market as much as possible. And that's also why our promise as a company is we do everything we do to contribute to unlocking a century of material innovation in the next decade. So at least speeding up this process 10 times. So try to get a new material in the market in, let's say, 1.5 years instead of 15 years. And as said a couple of times before, we strongly believe that AI will dominate the future of advanced materials, but especially if it can be trained on large experimental data sets. And I think the AlphaFold model developed by Google DeepMind is the best example to point towards. So it was an advanced AI model, but it was trained on this large open protein database that has been built in the past decades by scientists in the protein field. And because of this and this big, rich data set, it was able to develop a predictive AI model that could predict to 95% accuracy how a sequence of amino acids could fold. And this is really what inspires me and what I think we should try to adopt in many different fields. And because of that, I am also very positive that big companies like Meta in their Open Catalyst project are trying to build the AlphaFold model for electrocatalysis. And especially because electrocatalysis are something very close to VSP. It's one of the biggest material segments that we are working on. And it's also a key material domain in the inorganic space. I think if you want to solve climate change, then we need to crack the code of electrocatalysts, because electrocatalysts in the form of these thin film nanoporous layers are determining the performance of anything related to large scale energy storage through green hydrogen production, CO2 electrolysis, so the formation of e-fuels, but also next generation batteries and redox flow batteries are determined by our capability to develop and manufacture these thin film nanoporous layers. The only problem in this field is that there has never been in human history a period where big companies could find a time to invest billions into the development of a optimal synthesis process for thin film nanoporous layers. We do have magnificent technologies to create thin solid layers through PVD, CVD, ALD, all the technologies that have been developed for chip manufacturing. But if you want to create a thin film nanoporous layer, then you are still stuck in a decades-old process that has once been developed by the chemical industry. So you start with wet chemical synthesis of your powder, which is a time-consuming, complicated process. And then the second step is you do a wet coating process. So you mix your powder again with all kinds of chemicals to slot die coat it onto your surface, and then you put it into the oven to evaporate all the chemicals. And then after a 7-step process, you end up with some kind of porous structure being glued to your substrate. So this is also where VSP has spent most of our efforts in the past 10 years to develop this process from the ground up and try to develop the most optimal, simplistic, flexible, reproducible process to go basically in a single step from a solid inorganic material, press a button, and then out of the system comes this highly porous thin film layer that can be applied on all kinds of different substrates. So where VSP started off in the beginning, more focusing on our unique capability on gas phase synthesis of nanoparticles, I think we are more and more focusing our efforts on thin film nanoporous layers, which is a unique type of material that you can make if you're able to make the smallest, most stable and purest nanoparticles in a gas phase process. So what we have been seeing in the last months is that our technology has been very successfully applied by customers in the development of, for example, new low-loading iridium coatings for PEM water electrolysis. So PEM water electrolysis is one of the two main technologies for green hydrogen production, but it suffers a lot from the use of very expensive iridium. And we only produce roughly 7,000 kilograms of iridium on a yearly basis, which is not that much. It's half a cubic meter. And most of that material is already used in all kinds of different industries. And at the same time, we would like to scale the market of PEM water electrolysis massively in the coming years to really make green hydrogen a cornerstone in our new energy system. And this can only be achieved if we are able to achieve the same industrial performance with 10 times less iridium. And you can only reduce the iridium without losing performance if you have a much better precision in structuring your nanoporous iridium onto your membranes or your porous transport layers. So that's where some of our customers are heavily focused on. I think it's also an area of UL, RI to focus in this domain, and it's definitely a big part at VSP. I didn't want to go into detail what kind of performances we are able to achieve because we already covered that in other webinars. But feel free to reach out if you want to know more about this topic. The other part, which is also why we invited Stuart, is that we see customers, more and more customers, adopting the P1 to build these self-driving labs. And there I would like to spend a little bit more time explaining why the P1 is such a valuable asset if you want to build a self-driving lab for inorganic materials or for inorganic nanoporous materials for energy applications. So first of all, the standard P1 can be equipped with 2 nanoparticle sources, and it has a huge flexibility in the material space. So our core technology is making use of electrical sparks between those solid rods to evaporate the material. And at the spark, we created temperature going up to 20,000 degrees Celsius. And this gives us the capability to process so many different materials because all those materials will evaporate at such a high plasma temperature. And that also makes the system very useful because the processing is almost the same if you want to process gold, titanium, platinum, carbon. There's little difference in switching between those materials, which is something that is a big problem in chemistry. If you want to make gold nanoparticles, you have a completely different chemical recipe that you need to follow and optimize versus if you want to make a palladium nanoparticle. And sometimes you can't make your particle because the chemistry doesn't allow you to do it. The other thing is that because you are using 2 sources and we can control the output of both sources very easily by controlling the number of sparks, by controlling the energy per spark, and that by we can control the elemental mixture if we combine the outputs of both sources. So we can print a nanoporous layer where we have a predefined elemental composition between nanoparticles, in this case red, and nanoparticles green. And what we have been seeing in the past months that if you have this composite nanoporous layer, and if you heat it up to the right temperature, you can see the formation of a new alloy material without losing your porosity. You can imagine that if you increase the temperature too high, that your nanoporous material will collapse and will form a solid layer. But there is this intermediate phase where you can let's say, promote the alloying formation so that you don't have separated particles of red and green, but you have this new alloy being formed. Of course, that is all dependent on the material that you are trying to mix and whether or not they will form a new phase. But this capability that you can use two different sources, we can easily control the output of both sources. That gives us unique capability to control the elemental composition per dot. And then we can create those new, let's say, alloys by just simply doing a small heat treatment afterwards. Is the best process that I've seen so far in the inorganic material space to do high throughput synthesis of combinatorial materials. And I can show you an example of samples that we have been printing or that we are printing on a weekly basis. So here we have used two different materials, and every square that you see on the silicon wafer is a 2 by 2 millimeter, 0.25 milligrams per square centimeter loading of uniquely compositions. And we have printed the same compositions on the silicon wafer and on the GDE. So this is done for XRD analysis to really verify the formation of a new phase or this new alloy. And the GDE substrates are then used for electrochemical testing. This is for CO2 electrolysis. And to give you a bit of perspective on how the system then looks like if it's printing these samples, we have a nice time-lapse movie made. So again, this is a system with two sources. Every source has a different material. We are printing fully automatically different compositions. So these prints could take up 20 hours, 30 hours without any human interaction in between. There's just a single script. You set the system, you load it with the two different electrodes, you press the button, and then it takes 20 hours to print all those different material compositions. And then, yeah, you have your unique materials, your unique nanoporous materials that you can test. So this goes on for quite some time. But this is not the only thing that VSP is focusing on. So by just enabling the most advanced self-driving labs, screening huge material spaces in the inorganic nanoporous film space is already a big step forward. But we also care about translating those new materials as quickly as possible to mass manufacturing. So based on the same core technology, we are actively developing the P100 and the P1000, which are industrial scale production systems that should coat these nanoporous layers on, let's say, 15,000 square meters of substrate on a yearly basis. So our ideal is that you have screened new materials, and then overnight we can translate the printing recipes from our lab scale system to our industrial scale system, coating huge amount of surface areas with the same type of material the next day. And by really redefining every stage of material development, again, focusing on these thin film nanoporous layers, we really have the chance to crack this problem and bring the development time down from 15 years to maybe 1 year or maybe even less. So that was my short update. There's much more, let's say, news that we will be bringing out in the coming days, weeks, on proving our capabilities in this field. So next to this webinar, please stay tuned to get more insights, to get more data, to get more experimental results on these topics. Thank you.
Thanks a lot, Aaike. Thank you for that wonderful talk. I hope that you all got a deeper dive into our technology and its impact on accelerating material discovery. So next is the live Q&A. So please keep posting your questions in the chat for Stuart and Aaike. And if you could also just mention whom you're addressing the question to, that would be great. While you're posting your questions, I have another poll question coming up your way, because no topic is complete without talking about the challenges, right? So here is a question about the challenges. What is the biggest challenge that you faced in the establishment of your self-driving lab? There were some challenges, I think, mentioned in the talk today. Do you have something similar or do you have something different? Please cast your votes. And please also mention if you have something different. Feel free to mention that in the chat. Yeah, I see a lot of responses for material synthesis and material characterization. In fact, I see that most of them are all relevant challenges. Yeah. I'll give you a couple more seconds. Also, I'm reminding you to please keep posting your questions in the chat. All right. Thank you for those insights. Shall we go on to our live Q&A session? So I'll read the questions from the chat. I think the first question is addressed to Stuart by Pramod. Given the role of high throughput synthesis in generating vast amounts of experimental data, do you think that it's feasible to unify data from various automated labs to accelerate material discovery? And what kind of infrastructure would be essential to centralize and effectively manage this data across diverse high throughput platforms?
I think that's a great question. And in short, the answer is yes. But I think, embarrassingly, material science is decades behind our friends in pharma. And when it comes to automation, when it comes to big data, when it comes to machine learning, pharma has sort of led the way in all of this. At the moment, if you go to the literature and you just check a material, you'll find 3 or 4 different ways that are the best ways to make that material. And people report different aspects of the material, what they find important. So I think what needs to be done, and it's one of the things that we've had conversation with various parties about, is really understanding what that standardized data format looks like. So it may be that somebody's synthesizing a material and they're interested in the gas absorption properties of it, but it might be that someone else in another country is interested in the catalytic behavior of the material. So how do you start to standardize that and normalize it? I think, as I said, there's a lot of movement in this area, and there has been for several years. It will come. I just don't see it happening in the next year or two, but it's certainly something that's required.
Maybe to add on that, we also see this as a big topic at some of our academia customers across Europe and the US, that most universities, they have their unique infrastructure. They are good in a specific high-end material characterization process that none of the other universities have. So there is a strong interest to double down collectively on a single material synthesis process so that you can copy that same process at different institutes, create the same material, but then process that material to this unique material characterization process. And then if you combine the key knowledge from all those unique infrastructures into a centralized data set, you will get the most richest overview of that specific material. But it requires much higher levels on standardization. You already see it in electrochemical testing. If your cell is slightly different, if your pressure is slightly different, if your temperature is slightly different, all these things have a big influence on the performance and on your result. And in that part, the inorganic space has been very much farther away from getting there to the bio industry or synthetic biology space. And I think now we have found a possible path forward in rapid combinatorial printing of thin film nanoporous materials. I think there is a good reason to start standardizing all kinds of processy steps to make this cross lab correlation and comparison possible.
Thank you. Second question is to Aaike. Does the system have the capability to synthesize 3-element alloys with controlling the chemical composition?
So as you have seen, the printer is equipped with 2 sources. You could either make a pre-alloyed electrode, so then the rod that you put into the sources are already a pre-alloyed made of any combinations. So you can also make a pre-alloyed electrode of 5 or 6 elements, if that's possible. We have seen multiple times that spark ablation has been successfully achieving high entropy alloys. There are numerous applications or publications showing that. And especially high entropy alloys is opening up this new domain of very interesting material properties that you don't see if you just mix 2 or 3 materials. The other part is that the current printer is designed for 2 sources, which is already giving you quite some flexibility, as Stuart indicated. But we definitely don't want to stop there. So we are already thinking about developing the new printer, especially optimized for self-driving labs, that maybe could hold up to 8 or maybe even more sources. Because then you can mix and match on the fly even more different material compositions. But that's also much more complicated to make that into a easy to use, simple, reproducible process. So there we still need some time to develop that. But that are the type of systems we would like to develop in collaboration with, for example, Stuart Miller and others.
Yes. And the next question is to Stuart. You mentioned that you initially spent 12 months gathering various types of data when establishing the lab. Could you share how this data was processed and what decisions were made based on the analysis?
Absolutely, yeah. One of the earliest decisions and one of the first hires that we made at MDRI was a data scientist that didn't have any experience as a chemist. It was a very conscious decision because we can teach somebody chemistry, but we couldn't teach somebody the data science. We needed somebody to come in and really own the data science process. So in doing that and having someone that, and one of the things that maybe we don't want to admit to, but we as material scientists tend to have a preference towards a material type or an application type or a characterization type, and it biases the way that we look at our data. When you get someone that doesn't really understand the nuances of the material or the characterization, but is focused on the data and is focused on the numbers that the data gives you, that changes the way that you look at things. So we spent a long time working through with our data science team how data would be collected and what's important to us. And we were asked some questions that, you know, maybe we didn't really see the relevance in at the time, but they're critically important to how manipulation is done to, or how the data process is done. Where as a chemist, we would leverage chemical intuition, but we can then lean on data science to be able to do that. We also spent a long time speaking with instrument vendors and making sure that we either could directly integrate the instrument with our ELN platform or our LIMS platform, or whether the vendor would be willing to partner with us to help that implementation. Some of it's not been straightforward, but when we explain what we're doing to our vendor, with our vendors, and how the seamless data integration is critically important to what we do, that's been a key point on how we interact with vendors, and ultimately if we decide to move ahead with the purchase of equipment, because what we want is we want our data to flow directly to our LIMS and our ELN, rather than individuals being reliant on taking the data, going with a USB pen and picking up the data and taking it to their own instrument, their own PC. It all sits in a centralized cloud-based location for us, and having instruments that integrate with that has been critically important.
Thank you. A question to Aaike. Could you please comment on the bonding between the particles in the porous films, and how stable are the films to scratches or the like?
Yeah, so one unique feature about spark ablation is that it's enabling us or customers to make at room temperature the smallest possible inorganic nanoparticles. So most of our primary particles coming out of the sources are 2 to 3 nanometer in size. And at such a size, they have a very strong van der Waals force because of their size. And we can make great use of this van der Waals force to make them stick towards each other in these nanoporous layers, but also to make the nanoporous layer stick to the surface. Again, it's not the strongest bond, but it's strong enough to do post-processing and to do other steps. On the other side, we see that print the nanoparticles in the form of this nanoporous layer, we need to accelerate the gas flow at some point in the process to supersonic speed. And because of this very high speed, you will get partially sintering when the particles are being bombarded at high velocity on the substrate to form these nanoporous layers. So you will get some kind of neck-neck bonding or neck-neck welding between the particles, which further strengthens their inter-particle connection. The other part, which is about the next question, is about do you need to do post-processing after printing to get high electrochemical performance? We have seen many results where we didn't do any post-processing, where we see very top-notch performance. But we have also seen examples where additional heat treatment to strengthen the bonding in between the nanoporous layer and the support could definitely be beneficial by doing post-processing. But I do want to mention that it's not needed. We have had many great examples where we just printed iridium nanoporous layer without any post-processing, just assembled the cell and really saw very good stable performance.
Yes. And to Stuart, did you develop in-house LIMS software, or are you using a commercial solution to digitize and integrate the lab's various components? And what are the advantages of your chosen approach?
So we purchased a commercial solution. We evaluated several different vendors, and then we purchased it. And it's a little bit a different mindset from an academic approach, where really the value of the institute is leaning into that materials discovery rather than software development for a LIMS or an ELN. If I can buy the product off the shelf, then that frees up time in the materials discovery process. So it's trying to make sure that I can get the maximum return on my investment in the staff, the equipment that we have. I've seen a lot of self-made LIMS and ELNs, and they are remarkable, but it requires a lot of work to be able to do that. So our focus isn't developing the software, our focus is developing the materials.
And the last question to Aaike. Is it possible to use the VSParticle generator to design an alloy with controlled minimal porosity that maintains catalytic activity, making it easier to characterize by surface index and simplifying computational modeling?
Good question. So it's definitely possible to make a well-controlled alloy and also to control the porosity. So we know that different parameters, for example, the pressure difference between in the printing chamber and upstream, have a big influence on what kind of porosity that you will get in the end. But if this really makes it easier to do surface characterization by surface index, that I don't know for sure, but please reach out to us and then we can look into this with more depth with our experts.
Yes, like that, we are at the end of our session today. If you have any questions that were unanswered, or if you have any other questions, please reach out to us. And if you have any suggestions for what you would like to hear from us in the next webinar, please do mention that as well. And thanks a lot to Stuart, thanks a lot to Aaike for your time and effort. And thank you all the participants for your active participation and inputs. And I would like to mention that the webinar is recorded and you will receive the recording within a week. And if you have any additional questions, please feel free to reach out in the email address here and visit our website for more information. Thanks a lot and see you in the next webinar.
Thanks. Have a good day, people.
Thank you. Enjoy.